of inertia of a uniform rod of mass m, length l, about an axis passing through its end at an angle theta. Angle theta passing through end. Okay. About that axis, we need to calculate the moment of inertia. Let's take rod like this of mass m and length m. Now axis of rotation is somewhere here passing through one of its ends, and it is making an angle theta with the length of the rod. So it may be rotating like this with angular velocity omega. Let's do like this. Okay. So about this axis, moment of inertia of this rod we are going to calculate. As we know, moment of inertia of any rigid body system is integral of dm into r perpendicular square. We discussed already. Moment of inertia of any rigid body system is integral of dm and r perpendicular square. Okay. Now, what I will do is, first we know the moment of inertia of any point mass, which is m into r perpendicular square. So first I will take the point mass from this rigid rod or uniformly distributed rod, and I'll calculate perpendicular distance of that particular point mass from the axis of rotation. Okay. So here somewhere there is dm, small amount of mass. Okay. And I can express the value of this dm as c. In L length, there is m amount of mass. So in unit length, there will be m by L amount of mass. And in dx length, with small dx, where this I am taking as x from the axis of rotation. In a dx length, where dx is this small part, in the dx length, mass will be m by L into dx. Apo dm, mass in that small dx length is m by L into dx. Let it be. Now this point mass perpendicular distance from the axis of rotation. See, x is just distance, not perpendicular distance. So perpendicular distance will be like this. This is what perpendicular distance. Okay, which is r perpendicular. So now about this axis, dm amount of mass is there at perpendicular distance r perpendicular. So that moment of inertia will be dm into r perpendicular square. And if I integrate the total value from the starting to ending limit, moment of inertia of the complete rod will come. But before that, let us express r perpendicular value in terms of x or known values. See, from this triangle we can write, in the triangle. If I take sine theta from the above triangle, what we can write opposite by opposite to 90. This is what actually 90. So opposite to 90 is x. Upper r perpendicular will be x sine theta. This is our perpendicular. Now we have the value of dm, which is this, and we have r perpendicular value, which is this. And if I integrate this, I will get the moment of inertia of the entire rod about that axis. So let us take moment of inertia is integral of dm is m by L into dx into r perpendicular x sine theta square. Okay, so if you see this, m by L is constant, and also sine square theta, because theta is constant, so sine square theta also will be constant. Integral of x dx, where x square is x square dx. From where to where? From starting limit 0 to ending limit L. Look at the diagram. Here, starting value of x is this 0, and the ending value of that same x is this, which is L. So from 0 to L, if we integrate this, the value will be, so we can write m by L into sine square theta into x square dx, which is x cube by 3 for the limits 0 to L. So if I substitute the limits, m by L into sine square theta, upper limit L cube by 3 minus lower limit is 0. So if I take this, this value will be coming. 1L will get cancelled here. So it will be ml square by 3 into sine square theta. That is, moment of inertia of a rod about an axis passing through its end and making an angle theta with one of its ends is given by ml square by 3 into sine square theta. Now, if I take a case, let's say like note point, if I take a case, rod is like this of mass m and length L, and axis of rotation is like this, which means perpendicular to its length. Theta becomes what? 90 degrees. Aduk moment of inertia will be m L square by 3 into sine square 90, which is ml square by 3. Okay, in SI system, kg meter square. So moment of inertia of a rod about an axis passing through its end, making an angle theta is ml square by 3 into sine square theta, and perpendicular to its length, if axis perpendicular to its length, it will be ml square by 3. Okay, this is the case. Now one more derivation, let's see. After that, we'll see some applications based on this. That is, see next case, moment of inertia of a uniform rod, same, of mass m, length L, about an axis passing through its midpoint at an angle theta, at an angle theta. So the diagram looks like this: a rod of length L making an angle theta with its axis axis passing through its center. The same logic will apply. We'll take point mass at any x distance from the axis of rotation. We'll calculate the dm value, and from that we'll calculate the value of r perpendicular, and under integration dm into r perpendicular square will apply. See how it will be. From this axis of rotation at x distance, let's take small length dx, in which dm mass is present. Okay, and perpendicular distance of this dm will be like this. This is our perpendicular. Okay, so we know already dm value in previous case we calculated is m by L into dx. And we also know that our perpendicular value in previous case we calculated, which is x sine theta. Now total moment of inertia will be integral of m by L into dx into x sine theta the whole square. But limits, if you see clearly, see this point I am taking as a reference point or reference line. One part of the ring, one part of the rod is on the left side, and other part of the rod is on the right side. So obviously, the moment of each point mass on right side of the rod and the moment of each point mass of the rod on left side will be having opposite tendency. That means this limit I can take as minus L by 2, and this limit, the remaining half limit, will be coming out to be plus L by 2. So limits will be minus L by 2 to plus L by 2. That is the difference, nothing more than that. That is the difference for this case and previous case. So we'll take M by L and sine square theta as constants out, and under integration x square dx from minus L by 2 to plus L by 2. So if we simplify this, M by L into sine square theta x cube by 3 under the limits minus L by 2 to plus L by 2. Okay, x square dx is x cube by 3. So it will be M by L sine square theta upper limit L cube by 8. Let's take this 3 also out. Minus one more L cube is there which is having minus sign. So power 3 odd number. So it will be definitely minus value. Again L cube by 8. One more minus is there, no, as I told you. Upper limit minus lower limit, no, inga minus varum. So minus of minus becomes plus. So the answer will be 2L cube by 3 into M by L sine square theta. So 2L cube by 8 by 3 M by L sine square theta, in which 4 times it will get cancelled. So the final answer will be M L square by 12 sine square theta. This is what moment of inertia of the rod about an axis passing through its center and making an angle theta. As like I told you in previous condition, note point. What if the rod is making 90 degrees with the axis and passing through its center? Upon moment of inertia will be ml square by 12 into sine square 90, which is I is equals to ml square by 12. Remember direct conditions. If the rod is if the axis is passing through end of the rod, ml square by 3 sine square theta. If the axis is passing through center, making an angle theta, ml square by 12 into sine square theta. If the rod is perpendicular to axis of rotation, passing through end, ml square by 3, passing through center, ml square by 12. By using these two conditions, let's solve some questions. By using these two conditions, let's solve some questions. And then we'll go to next derivation. Okay, so just have a look, just 2 minutes, have a look what we did. Just have a look. If any confusions are there, you can ask me. Have a look for 2 minutes. So that how we approached the perpendicular distance, how we calculated dm, and then how we substituted in this condition and how we integrated. Next condition. So the major difference for the axis passing through end of the rod and the passing through the center of the rod is limits. Okay, limits in end case is different from the limits in case of center. Nothing more than that. So derivation part is not important for NEET students. Okay, but the final results of the both the cases is very important. See, have a look here. The almost everything is same. Just we took the limits from minus L by 2 plus L by 2. Nothing more than that. Okay. Yeah. Now let's try a question from this. Okay, both passing through end, passing through center. If I take a situation, two rods are perpendicular to each other. Both are of having same mass and same length, m and l. And axis of the rotation is like this, in the same plane like this, exactly passing through center. Okay. Then what is the moment of inertia of the system about this axis? If it is rotating like this, what will be the moment of inertia of this system completely? Think of it once you just have a look like how to solve. If anybody can solve, think. Anybody can tell me the answer? Any one of you? See, obviously this angle will be how much down? 45 degrees. Because both are of same length, so it makes a sense of square. So which means this angle will be the angle of the diagonal, which is 45 degrees. At the same time, this will be 45 degrees. Now think like this. Axis is for this rod. Axis is passing through its end and making an angle of 45 degrees. The moment of inertia of this rod will be ml square by 3 into sine square 45. What about moment of inertia of this rod? ml square by 3 sine square 45, because the same scenario that it is also having. So total moment of inertia will be ml square by 3 sine square 45, 1 by root 2 whole square into 2 times of that one. So it will be ml square by 3, because root 2 whole square is 2 and 2 will get cancelled. Okay, this is the total moment of inertia in SI system. I hope you understand. Is it clear? One more question. One more question. Let's try. Let's take a letter N from the word NEET. Okay. N letter I'm taking. So here this angle is given 60 degrees. At the same time, this angle is given 60 degrees. Right? Now there is one axis of rotation of this N passing on the top of the letter N like this. And the system is rotating like this with angular velocity omega. So now my question is that only, what is the total moment of inertia of this letter N if each part of this N is having mass M, length L, mass M, length L, mass M and length L. You have to solve it and post the answer in message. Make it fast. I'll give you just 2 minutes time. Make it fast. Purida, are you there or left the class? Try. I'll give you 2 minutes time. Anybody got the answer? 2 ml square by 3. இது எதுக்கு? ப்ரீவியஸ் கொஸ்டினுக்கா? தப்பு. Okay, see. Now, பாருங்க, axis is passing through its head. I mean, edge, end. This rod, if you see, it is making an angle 90 degrees. தனித்தனியா பாருங்க. இப்படி ஒரு ராட் இருக்கு, இப்படி ஒரு ராட் இருக்கு, இப்படி இன்னொரு ராட் இருக்கு. சரியா? ஓ, இது ஆக்சிஸ், இதுக்கு இது ஆக்சிஸ், இதுக்கு இது ஆக்சிஸ். Okay. So at what angle this axis is there? For this 90 degrees. For this it is 30 degrees. Because it is 60. And here it is 90 degrees. So moment of inertia of this is ml square by 3 directly. Moment of inertia of this ml square by 3 sine square 30. Moment of inertia of this ml square by 3. Now it is total moment of inertia 2 ml square by 3 plus ml square by 3 sine square 30, which is 1 by 4. Now ml square by 3 you take out of 2 plus 1 by 4. So it is 9 ml square by 3 into 4, where it will go 3 times. It is 3 ml square by 4 kg meter square. Rida, so you may have doubt that why we should not take this angle into consideration. Why we should take only this angle. See, when I say that the perpendicular distance with axis of rotation of this rod, so axis of rotation இப்படி தானே இருக்கு. So when it is rotating like this, the perpendicular distance sense will be in this condition only. Okay, perpendicular distance to the rod. இப்படி. Understand? Or perpendicular distance to the like this. Okay, if you go this side, it won't be, at any case, it won't be perpendicular. It won't be any perpendicular distance. It won't be any perpendicular distance. So in the pakkan chance aayega. So remember like that. One point you can remember as which side that the rod is bending from the axis of rotation. That side angle is to be considered in the application of moment of inertia of any rod about an axis at an angle theta. Because perpendicular distance, to take the perpendicular distance, the better chances will be on that side only. Okay, I hope you understand. Next let's go to, okay, one more derivation. After this we'll see questions after discussing parallel and perpendicular axis theorem. Again we can come back to the concept of rotation of rods, no problem. Still two more derivations are there, like moment of inertia of a ring, moment of inertia of a disc. After that derivations we will not do, because similarly we can write remaining applications also. So let me complete the next two cases also. Next case is moment of inertia of a uniform ring of mass m, length L, about its own axis. It means what? What is own axis means? Remember, questions they will say, or sometimes in statements they will frame like moment of inertia of a rod about its own axis, moment of inertia of a ring about its own axis, moment of inertia of a sphere about its own axis. Generally, The term own axis means that axis is perpendicular to the plane of rotation. The plane of rotation. And it must pass through, it must pass through center of mass. I hope you understand. It must pass through center of mass. Generally, in the plane of rotation, or would require plane of rotation, that will be only valid or available for two-dimensional laminas, 2D laminas, and so on, two-dimensional bodies, like a ring or disc or plate or sheet, that type of cases. If you take the sphere, like hollow sphere or solid sphere, okay, every axis passing through center of mass will be a own axis, because whatever the axis it is, if it is passing through center of mass, about that if it is rotating, that becomes the plane of rotation. But for a disc and rod or sheet, such type of cases, it won't be same. It won't be same. If I take a disc case or if I take a ring case, axis passing through center and perpendicular to the plane will be only one possible case. Because see the case, see the situation. Let me explain this clearly. If I take a ring, axis passing through center or center of mass, axis passing through center or center of mass, axis passing through center of mass. All these three axes are passing through center of mass only. But only this dot, which is into the plane, is perpendicular to its plane, which is perpendicular to its plane of rotation. But this x-axis, which is passing through center, will not be perpendicular to the plane. So this and this are not own axis. Only z axis will be the own axis. Because this must be very clear for the cases of two-dimensional lambdas. 3D case, 1D case, it's not necessary, because every axis passing through center of mass will be own axis itself. Okay, it will become own axis only. But for 2D laminas, the condition must be axis must pass through center of mass as well as must be perpendicular to the plane of rotation of the body. Remember it. Now the case that we are going to solve is a ring of mass m and radius r is there, and its axis is passing through its center of mass, which means center because it is uniformly distributed mass, and the ring is rotating in such a way that the axis is perpendicular to plane of rotation. அப்படின்னா எப்படி இருக்கும்? The case will be like this. Okay, this is the axis. I mean, in this plane, into the plane, into the plane. Okay, so same method we follow. Like we'll take small point mass on the ring and we'll calculate moment of inertia of that, and we'll calculate perpendicular distance. Sorry, we'll take the small point mass of the ring and we'll calculate the perpendicular distance from the axis of rotation to that point mass, and then we'll integrate to get the total value of moment of inertia. Let's see how to do it. Okay, so as I told you, here I'm taking a point mass which is dm, where I know total mass is m and radius is r. Sorry, here I wrongly wrote that length L. It is not length, that is radius. Okay, now it is rotating like this. So perpendicular distance obviously r only. Upon moment of inertia, we can write integral of dm into r square. Very simple. But what is that dm? Integral of dm is what? Total mass. Then here, many point masses will be available. If I add up all those point masses on the ring, what it will be? M. So moment of inertia of a ring about its own axis, which we will call as center of mass axis, is m r square. Is m r square. Moment of inertia of a ring about its own axis, if its mass is m and radius is r, is nothing but m r square. Okay, about this type of axis passing through center but along the diameter, passing through center along the diameter, அந்த கேசஸ்ல இருக்கிற மொமெண்ட் ஆஃப் இனர்ஷியா எப்படி கால்குலேட் பண்ணணும்னா அதுக்கு தனியா ஒரு ரூல் இருக்கு. லைக் parallel axis theorem, perpendicular axis theoremனு செப்பரேட் கான்செப்ட் இருக்கு. அது முடிஞ்சதுக்கு அப்புறம் you can understand how to do it. Okay, so till that parallel axis theorem and perpendicular axis theorem, you just understand how to calculate or what is the value of moment of inertia for an axis passing through its center of mass and perpendicular to its plane of rotation, which is mr square. Okay, based on the same logic, based on the same approach, let's do for the case of a disk. Okay, so simply you can keep writing as moment of inertia of a uniform disk, uh, disk mass m, radius r, about its own axis. Same case, its own axis. I hope you got it. So scenario we can take like this, like there is a disk. See, I'm drawing the diagram like a side view. It's not front view. Front view also I'll show you. First front view let's take. இது ஃபுல்லா டிஸ்க் மாஸ் டிஸ்ட்ரிபியூஷன் வந்து ஏரியல் டிஸ்ட்ரிபியூஷனா இருக்கும். இட் வில் பி ஏரியல் டிஸ்ட்ரிபியூஷன். ஃபுல்லா மாஸ் இருக்கு. இதோட மாஸ் m, ரேடியஸ் r. So axis is here passing through center. ஓகே, இது ஃப்ரண்ட் வியூ. சைடு வியூல இருந்து பார்க்கும்போது when you see it from side view, it will be like this. Okay, mass m and radius r. இது ஆக்சல் இப்படி ரொட்டேட் ஆகுது. ஓகே, சைடு வியூல இருந்து பார்க்கும். So logically same integration formula we need to apply, but here the approach of integration will be little different. Like what I'll do now, I'll take this disk as a combination of rings because I have the information of moment of inertia of a ring about its own axis. So what I feel here is if I take a disk as the combination of so many rings of different radius, different radii, one ring moment of inertia I'll pick somewhere in this disk part, and that value I'll integrate from starting limit to ending limit. That is what I'm going to do. I think in electrostatics recently also we discussed a concept called electric field due to a disk of charge by using the electric field due to a ring of charge. By considering electric field due to ring and by taking the disk as the combination of rings, we integrated the value of ring electric field from starting radius to ending radius, and we have got the value of electric field due to disk. Exactly same, exactly like that. I'm taking a ring or a ring part in this disk, in this complete disk. I'm taking a ring part of radius small r. Okay, and this moment of inertia and the moment of inertia of this ring I can write as mass of that ring part into r square of that ring part. And if I integrate that value from 0 to capital R, because the starting ring I can take at the center with 0 radius, and the ending ring I can take at the circumference of the disk at the radius r. So my approach will be moment of inertia of a disk is nothing but integral of moment of inertia of ring part. Ring part. From where to where? From r is equal to 0 to r is equals to capital R. But ring part moment of inertia, how to calculate? Yes, moment of inertia of, let's take dI bro. Okay, ring part, ring part. Ring part now, ring part would a mass, which is dm, into ring part would a radius square. Yes, how to calculate the ring part mass? Very simple. I know the total mass is m, which means in a pi r square area, there is m amount of mass. Then in unit area, how much mass will be there? M by pi r square, of course, areal mass density. Then what is the area of this ring part? Ring part, it is one dimension case, but we want area. Then what we will do? We will calculate the length of the ring and we'll multiply it with thickness of the ring, which is 2 pi r into dr. So dA, which means ring part area. ring part area is what? 2 pi r, this the circumference length, into thickness dr. If I take this small thickness as dr, then the total area of that ring part will be what? 2 pi r into dr. So in unit area, m by pi r square amount of mass is there. Then in this ring area, how much mass will be there? How much mass will be there? M by pi r square into 2 pi r into dr. So pi and pi will get cancelled. So mass of the ring part is how much? M into 2m into r dr divided by r square. Now we have got mass of the ring part, and we also know about the radius of the ring part. Then if I substitute here, okay, dm into r square from 0 to capital R, it will be integral of dm is 2m r dr by capital R square into again small r square from 0 to R. Take the constants out. 2m by r square is constant. Here one r, here r square, r cube dr, which is r power 4 by 4 for the limits 0 to capital R. If I substitute it, 2m by r square into upper limit r power 4 by 4 minus lower limit is 0. So in the r power 4, r square times will get cancelled. Then it will be 2 times. Then what is left? M capital R square by 2, which means moment of inertia of a disk about its own axis is mr square by 2 in SI system, kg meter square I'm writing. Okay, so now finally, overall conclusion, if we see, moment of inertia of rod about its end, about its center at an angle theta perpendicular to its length. Rend cases. Total 4 cases we have seen there in the rods itself. And moment of inertia of ring about its own axis is mr square. And moment of inertia of disk about its own axis is mr square by 2. By using this information, we can even calculate moment of inertia of hollow cylinder, hollow sphere, solid sphere, and sheet of charge. All these derivations can be done based on the same logic, whatever we approached till now. So, no need of further derivations for the other cases. For NEET students, if it is JE, hollow sphere and solid sphere derivation somewhere it is useful for the advanced exam. But for NEET students, this information is enough to remember the conditions for the further cases like remaining 2D or 3D or 1D laminas. So I'll give a list of moment of inertias of all rigid bodies, which is very important and you must remember until your NEET exam. Okay, so let's make a small table. Okay, in that I'll write moment of inertia of important cases for NEET. Okay, so first I'll take the shape in the table, shape of the object, the rod, illana, ringa, sphere, everything. Then moment of inertia about center of mass itself, let us write. Okay, moment of inertia about center of mass. You will get the clarity. And let us take the view of it, diagram of it, how it looks like in applications. Okay, first one, let's take rod of length L, mass M. Bracket about end. I clearly mentioned center of mass X on the theta condition varadidla. So we can write ml square by 3. Diagram எப்படி இருக்கும்னா இப்படி இருக்கும். Sorry, it's end now. I took it center. 1 minute. It's about end. Yes, like this. Next, second formula வந்து I'll take for the same case of rod of length L, mass M, about center. Formula we know, which is ml square by 12, center of mass axis. So it looks like this. Next, ring, as we discussed now. Moment of inertia, ring. Of mass m, radius r. About center of mass only now. Okay, about center of mass axis, if we take the center of mass, the center of mass, you just have a look. It will be m r square. It looks like this. Next, fourth one, disk of mass m, radius r, which is mr square by 2. Looks like this. இதுக்கப்புறம் you must remember all the cases. இதுக்கப்புறம் think like this. First, I'll go with hollow sphere. Hollow sphere. Before hollow sphere, let's take the case of cylinder. Hollow cylinder. Why you'll understand. Of mass m, radius r. Surprisingly, the value of that also mr square only, because இப்படி புரிஞ்சுக்கோங்க. If I arrange rings one by one, first ring and then second ring and then third ring and then fourth ring and then fifth ring, one by one rings if I arrange, definitely it will be making a shape of hollow cylinder then, like this only, hollow cylinder. It is indirectly like here one ring, here one ring, here one ring, here one ring, here one ring. So sum of all the moment of inertia of all the rings is hollow cylinder. So first ring mr square, second ring mr square, third ring mr square. Like that, n rings are there. N into mr square. N m you take as total mass of the cylinder into r square. One ring mass, let's say small m. Like that, n number of rings are there. So total n into m will be the total mass of the cylinder, which is m. Again, I'm taking capital M, let's say, into r square. Okay, like this. Next, sixth case, solid cylinder of mass m and radius r. Exactly. As you are thinking, it is mr square by 2 only. Because again, the solid cylinder is nothing but the combination of disks only. So one by one disk, if you arrange, again the same story. It will make a cylinder. So it will be mr square by 2. Next, seventh one I'm writing. Hollow sphere of mass m, radius r. You have to remember it. It is 2 by 3 mr square. Derivation is there for this, but not necessary. Just remember the value. If anybody wants derivation, I can explain how to do it. I'll explain how to do it. Next, solid sphere of mass m and radius r. It is 2 by 5 mr square. Solid sphere na ipdi. Okay. Apart from this, one more case is there. Sheet of mass. Sheet of mass. Mass m, length L, breadth B. I'll tell you how it will be. It will be m by 12 of L square plus B square. Okay. It will be looking like this. Length L, breadth B. Moment of inertia we are taking about its center of mass axis. Let's see like this. The derivation of this part we can do by using the case of rod. At the time, I mean, after completing parallel axis theorem and perpendicular axis theorem, you will understand how this n by 12 L square plus B square has come. Okay. So மொமெண்ட் ஆஃப் இனர்ஷியா எப்படி கால்குலேட் பண்ணணும்? ரிஜ்டு மாஸ் சிஸ்டம் இருந்தா மொமெண்ட் ஆஃப் இனர்ஷியா எப்படி கால்குலேட் பண்றோம்? எப்படி கால்குலேட் பண்ணணும்? அதுக்கு ஐடியாக்காக தான் இந்த 4 டெரிவேஷன்ஸ் நான் பண்ணிட்டேன். டெரிவேஷன்ஸ் ஆர் நாட் இம்பார்ட்டன்ட் as I told you, பட் ஃபைனலா நம்ம ஒரு லிஸ்ட் எடுத்துட்டோம்ல, மொமெண்ட் ஆஃப் இனர்ஷியா ஆஃப் ராட், டிஸ்க், ரிங்கு, ஹாலோ ஸ்பியர், சாலிட் ஸ்பியர், அதுல இருக்கிற ஒரு ஃபார்முலாமே இம்பார்ட்டன்ட். ஐ மீன் without knowing those formulas, it is not possible to proceed the problems of moment of inertia. So definitely you must remember all these 9 formulas of moment of inertia of rigid mass system. Okay, so I hope you understand. Just have a look. Any doubts there you can ask. Okay, 1 minute, just a minute. Yeah, Priyadarshini.